Hello, welcome to Petrochronix, a research group and extension project focused on petrochronology and its geodynamic implications.
We are a group based in Brazil that also has an international network of collaborators. They presently reside in Brazil, Australia, Finland, Germany, Italy, Switzerland, and the US.
Petrochronology involves several areas of the geological knowledge. We seek to disseminate it in a judicious yet clear and accessible manner.
In our researches, we use macro and microscopic observations, combining fieldwork, detailed petrography, thermodynamic modeling, processes dating, geochemical characterization, and much more.
From the natural record, we seek to characterize and quantify petrological processes in representative samples, generating comprehensive datasets that are interpreted considering the geodynamic processes that govern the Earth system.
We want to share research, from the basic concepts to the state of the art, promoting courses, spreading work results, and providing collaborations between institutions and people.
We understand that open science is vital to take down barriers to knowledge, and we prioritize the collaborative and open nature of our research. We also propose discussions on integrity and responsibility in the scientific environment.
As values, we believe in diversity, representativeness, and access to information. We seek to mirror these values in our initiatives.
On the YouTube channel, we promote the PTT Talk series, which are presentations on methodologies and advances in cutting-edge research with petrochronology.
Our actions also include the organization of lectures, courses, workshops, and meetings open to the community.
On Instagram and Twitter, we share, on Tuesdays, photos of outcrops and rocks in the field, illustrating geodynamic processes.
And, on Thursdays, photos of thin sections with microscopic features with interesting minerals and textures, reflecting different reactions and petrological processes.
So, if you work with petrochronology or are interested in related topics, be sure to follow us and get in touch. We want our community to grow even more. See you!
Hello, everybody.
Hello.
We are live with another PTT Talking. Maíra will start to present of the group today here. Maíra, yes, now it's okay. We can hear you. No, start again.
Right.
Oh, no. It's not to work. Kai, you can... It's just Maíra? Or...
I think so. Can you... Yeah, no, I think... Can you try again, Maíra? To speak?
Well, maybe you go out and come. Sorry, people, some troubles. Wait a minute to Maíra. Enter again.
Can you hear me now?
Now it's okay.
Okay, now I can hear you too.
Yes. And Maíra.
Can you hear me now?
Now,
Thank you. So, hello everyone. Welcome to our 2025 PTT Talks series. We are very happy to have Dr. Mona Lueder today with us. I'm Mayra Tedeschi from the Geological Survey of Finland, and today I'm with Mariana Madeira. She is a PhD student from UFMG, Federal University of Minas Gerais, and Catarina da Paz, which is a master student from University of São Paulo, and with Carlos Ganadi, or CAE, which is a researcher from the Geological Survey of Brazil.
well, I will give a brief introduction to the Petrogenetic Research Group. We are a team of researchers working with petrology, geochronology, and geodynamics to understand how the Earth's crust changes over time. Our researchers combine fieldwork with techniques like isotopic dating and thermobarometry, focusing on the tectonothermal history of rocks and mountain belts. One of our main activities is the PTT Talk, a space to share ideas and researchers with Brazilians and international scientists. You can follow us on social medias. Here we post about our talks, publications, and other activities related to the group. Now I will pass to Mayra again, talk about our 2025 PTT Talk series.
Yes. So hosted by us, the members of the Petrogenetic crew, with special guests, we have this YouTube series that bring together researchers from across the globe to share and discuss the latest discoveries of petrochronology, geodynamics, and other relevant fields. And we are very happy to be back to this season. So we have some very nice selection of talks until the end of the year, and that you can follow on our social media. And we are opening this season then with Mona Lueder. We are very happy for that. And Catarina will give some introduction about Mona.
So thank you, Mayra, and hello, everyone. Good morning or good afternoon. So thank you, Mona, again for accepting our invitation. I would like to give a brief introduction about Mona's background. Mona has a master's degree from the University of Potsdam, Germany, obtained in 2021. And she also has a PhD from the University of Bern, Switzerland, under the supervision of Jörg Hermann and Daniela Rubato, obtained in 2025. And now she is currently working as a research assistant in petrology and geochemistry at the same institution. And her research on hydrogen and trace element systematics in Rutile, looking at inter and intergrain variabilities, aims to develop rutile trace elements geochemistry as a tool for probing the metamorphic recording and understanding earlier process. Since 2022, she has been a member of the Geoscience Diversity and Equity Switzerland group, serving as a secretary and a member of the executive board from 2023 to 2025. And now I'll hand it over to Kawe, who will introduce today's talk.
Hello, everybody. Thank you for the invitation to be here. So Mona is going to speak to a talk that I love very much. Yeah. So we know that the onset of plate tectonics is hot debated in the earth science, and modern plate tectonics they give rise to certain kinds of rocks that are very rare in the geological rock record, like low temperature, high pressure rocks such as eclogites and ultra high pressure rocks. And so as these rocks are very rare in the Precambrian context, we have to find some other tools to investigate how the process related to subductions can be tackled. So there are a bunch of questions about this, such as how and if the code subduction really start in the Neoproterozoic, or if it's a preservation bias from the geological record. And so rutile it's an accessory phases on these rocks, and they can provide some information such as temperature and time, and together with trace elements, they can be a very powerful tool to understand this process. So, and as Mona is gonna say, rutiles also can have water in its structure, despite being an anhydrous phase, and this is very important as water increases in cold environments. And so let's see what Mona can show us. So I wish you a very good talk, Mona, and I'm excited to see your presentation.
Thank you, Kai. I will share the presentation here of Mona. And in the end of the presentation, we will have some times for questions. So take your questions here. Well, let's go.
Thank you so much all for the introduction and for the invitation to give this talk here. As Kai already hinted at, I'm going to talk about water in rutile and how we can use that for trying to find evidence for modern style cold subduction conditions. Our modern Earth is characterized by the presence of a global interconnected plate tectonic regime, which at modern times is characterized by the presence of modern style cold subduction zones. These are indicated by the formation of or by the presence of relatively cold thermal gradients, and with that, the formation of low temperature eclogite facies rocks to ultra high pressure metamorphic rocks. However, this wasn't always the present tectonic regime throughout all of Earth's history. So this is basically a schematic of how we think that the tectonic regime on Earth has evolved from in the Hebridean, a much hotter Earth with a very thin protocrust and a very thick magma ocean, and only successive cooling of the Earth allowed for the tectonic regime to evolve up to what it is now. So first, it developed a vertical lid tectonic with a stagnant lid. There are different models that try to describe how this tectonic regime could have looked like. One idea, for example, is plume and drip tectonics. And then cooling of the mantle let this evolve into a flat subduction, but first with a relatively flat, low subduction angle, and therefore relatively warm thermal gradients. And only, again, successive cooling of the mantle made it possible for the subduction angle to become steeper, leading to the formation of modern-style cold subduction zones. The oldest preserved geologic evidence in the shape of actual preserved rocks is about 600 million years old from ultra-high pressure metamorphic rocks. So the question is this evidence for actual onset of modern style cold subduction around this time, or is it a preservation bias? And can we maybe find evidence for when and how these different tectonic regimes on Earth have evolved? For this, what you can see here on this map is basically a compilation of preserved Archean and general Precambrian rocks. So you can see in the pinks and purples, this is where we can find Precambrian rocks on Earth. And you can see that is quite a bit of material preserved. However, very few of this is actual metamorphic rocks. And you can see that even fewer of that are eclogites, which are indicative of subduction in this case. So the oldest ones the oldest eclogites that we know of that are subduction related are at around 2 billion years old, and the oldest actual cold subduction related rocks are these 600 million year old rocks that we have. However, as you can also see in the oranges here, there is a vast amount of sedimentary units that can potentially preserve the eroded equivalents of previous Precambrian metamorphic rocks. So one way that we can basically try to fill in the gaps in our geological record is by looking at sedimentary equivalents of potential Precambrian metamorphic rocks. So if we want to do this, if we want to try to understand the evolution of plate tectonics by looking at the sedimentary record, we need to look at detrital single grains, and we need to be able to determine pressure, temperature, time of formation, and salt lithology from detrital single grains. And one prime candidate to do that with is rutile. Rutile is a very common accessory mineral at in high-grade metamorphic rocks, and it's also very stable during sedimentary transport. And on top of that, it can incorporate a variety of trace elements depending on the formation conditions and environment. So, for example, we can use zirconium iota thermometry, we can use uranium-lead dating, and we can use a variety of trace elements to try to identify salt lithologies. What's, however, been missing so far is a pressure indicator. And I've been looking into water in rutile as such a potential pressure indicator that we could then combine with other trace element signatures in order to try to understand or try to identify cold subduction signatures in detrital rutile. So if we want to do this, if we want to use rutile as a potential pressure indicator, there's a few questions we have to answer first. So if we want to answer if there's any evidence preserved in rutile for modern style cold subduction, we need to first see if water incorporation into rutile is actually pressure sensitive. And to be able to evaluate that, we need to start by looking at how much and in which way is water even incorporated into rutile in the first place. And this is where I want to start with. So how do trace elements get incorporated into rutile? So in this a little overwhelming figure that was supposed to come up one part after the other, but doesn't work here. So you can see basically a schematic sketch of the rutile structure. Rutile is titanium 4+ cations and oxygen, but it's also very prone to incorporate a variety of trace elements through substitution for titanium cations. If that's tetravalent cations, as here on the bottom left in this purple, that's very straightforward through a direct substitution of titanium 4+ with a tetravalent cation. However, other cations require charge balance and therefore coupled substitutions. So, for example, a trivalent cation and a pentavalent cation can be substituted together for 2 titanium 4+ cations, then again preserving the charge balance. Similarly, 2 pentavalent cations can go with a divalent cation, and also di and trivalent cations can be incorporated through the formation of an oxygen vacancy, as you can see here in the top, in the middle of the sketcher, where 2 trivalent cations being substituted for 2 titanium cations would then lead to 2 charge deficits that can be balanced by the removal of an oxygen out of the crystallographic structure and therefore the formation of an oxygen vacancy. But trivalent cations can also be charge balanced by the coupled substitution of hydrogen linked to these cations. In this case, as you can see here on the bottom, the titanium is substituted for a trivalent cation, and the hydrogen is then incorporated onto an interstitial site, leading to the formation of an OH bond with an oxygen in proximity of that trivalent cation. That similarly works for divalent cations, where 2 hydrogen are necessary for charge balance of the divalent cation. And hydrogen can also be incorporated, as you can see here on the bottom right of the figure, through a proton-polaron exchange, where titanium is reduced to titanium 3+, and simultaneously hydrogen is incorporated onto an interstitial site close to that. Now, as this OH bond sits in the A-axis plane, and rutile is a tetragonal mineral, we have a small problem when we're trying to analyze water in rutile by Fourier transform infrared spectroscopy, so FTIR spectroscopy for short, because what we get is a very strong anisotropy. This you can see here on the right in this example. So as you can see, there's virtually no absorbance when we measure parallel to the C-axis, and maximum absorbance when we measure perpendicular to the C-axis. This means that conventionally, rutile has to be separated and oriented prior to FTIR measurements. However, as petrologists, we always like to keep textural context, which means that we would like to be able to measure and quantify the water contents in rutile without the need for prior orientation. And this is what I've started my PhD with, basically trying to develop a method for in situ FTIR spectroscopy. So for this, we have to think about crystallography for a second. So if you imagine the indicatrix of rutile, so the indicatrix is basically a way that we can visualize the crystallographic structure or the unit cell of a mineral. For rutile, as rutile is a tetragonal mineral, the indicatrix is an ellipsoid with a circular base. And if we now have a randomly oriented grain in our thin section, this random orientation can be visualized as a randomly oriented cut through this ellipsoid of the indicatrix. The resulting cross-section is an ellipse with the A-axis as semi-minor axis. And if we do now polarized FTIR spectroscopy with a varying polarization angle from 0 to 180 degrees, at some point we're going to measure along this A-axis, which means that we are able to measure the A-axis spectrum directly, which is what we need for quantification. So using polarized FTIR spectroscopy should allow us to get precise quantitative water contents of rutile. So to test this, I've looked at 3 metapelite samples from the Central Alps. These samples all have quartz veins with large centimeter-sized rutile grains in them. What I've done is I've separated these large rutile grains. I've done oriented cuts to be able to measure the A-axis spectrum and the C-axis spectrum as well. And from the rest, I've taken some and I've crushed it to get basically unoriented or randomly oriented grains. And then I've done FTIR spectroscopy on these oriented and unoriented cuts. And these are the results I get from this. So as you can see here on the left, so this is a compilation of the FTIR spectra, more precisely the water region. In the purple on the left, you can see the C-axis spectrum where we see no absorbance, and the A-axis spectrum where we see a wonderful absorbance spectrum. And then in orange, you can see all the polarized measurements from 0 to 180 degrees at about a 6-degree step. And you can see that the water contents increase before decreasing again, with a maximum here in pink shown. And if we quantify the water contents for the A-axis spectrum and this spectrum with maximum absorbance, we get the same water contents with an error. And I've repeated this for multiple grains and for multiple samples. And this is a consistent result that I get, which means that using this polarized technique, we can actually get precise and accurate quantitative results using in situ FTIR spectroscopy. Now, I also wanted to constrain which defects we can identify from the FTIR spectra. So for this, I've looked at a large set of samples. Here, I just want to show you 4 examples from a high temperature eclogite, from a vein in a low temperature eclogite, an ultra high pressure white schist, and a hydrothermal vein. And I just want to mention here, most of my samples were collected by other people that kindly donated their samples to me, which I'm incredibly grateful, because otherwise I would probably still be running around in the field trying to collect enough samples for my work. So I just want to say a big thank you to everybody who gave me their rocks to work with. Anyway, so here I want to just show you the FTIR spectra from these 4 examples. And this is what you can see here. So as you see, there's all 4 spectra look vastly different, with 7 trace element related hydrogen defects that we can identify overall in that entire data set. 4 of these defects we know from the literature. There have been experiments done on synthetic trace element doped rutile that were hydrated experimentally. And from this, we were able to identify the defects related to titanium 3+, iron 3+, aluminum 3+, and magnesium 2+. However, if you look here at the right, that leaves us with 3 more defects that have never previously been described in the literature. So trying to identify this, we draw on the fact that there is a linear correlation between the ionic radius of the cation related to the hydrogen defect and the wave number of the OH band that we see in the FTIR spectrum. And this is what you can see here on the right. So we know the defects related to titanium 3+, iron 3+, and aluminum 3+. You can see that they fall nicely on a more or less linear correlation. And if you look at the spectrum here on the bottom of the hydrothermal rutile, you can see that there is another band in between the aluminum and iron related defect, which, based on what trace elements are in high enough content in rutile to be able to cause potentially a hydrogen-related defect, we were able to identify this as most likely being related to vanadium 3+, which leaves us with 2 more bands. And these you can see in the example of the high pressure vein here on top of the spectrum. You can see that those are at relatively higher wave number, and in fact at higher wave number than the magnesium 2+ defect that we know from the literature. And they also have a significantly broader peak shape compared to the ones related to titanium 3+, iron 3+, and aluminum 3+. This tells us that these defects are most likely also related to divalent cations. Now, again, based on which trace elements are in high enough abundance in rutile, we were able to infer this slightly different linear relationship, identifying these 2 defects as being related to chromium 2+ and iron 2+. If we look, I'm sorry for the text here, that was not supposed to look like that. So if we now look again at our entire data set, we were able to identify those 7 trace element-related defects. But these defects have varying contributions to the overall water contents in our rutile, depending on the sample. So as you can see here on the bottom right, the most prevalent defects are hydrogen related to titanium 3+ and iron 3+, which occur in all rutile. Aluminum 3+ related hydrogen is very common in metamorphic samples, while vanadium 3+ only occurs in hydrothermal and pegmatitic rutile. And hydrogen related to divalent cation defects we only see in rather reducing conditions and are therefore less common. So now that we're able to measure water in rutile and identify the exact hydrogen defects, let's have a look at whether water incorporation in rutile is indeed pressure dependent. For this, I've decided to do some experiments trying to hydrate rutile, because in natural data sets, you saw there is a lot of complexity involved in the spectra, and we would like to be able to look at pressure as a variable on its own without it being potentially influenced by other variables. So therefore, I've decided to do some piston cylinder experiments trying to hydrate rutile. So I've used rutile with 3 different compositions, 2 of which were pure rutile, one that is labeled as low defect rutile here, with relatively lower cation impurities. And then the last one was chromium doped at 200 ppm chromium. So overall, on molar basis, a similar amount of cation impurities as one of the pure ones. And I've run the experiments at 2 different temperature conditions, 2 different pressure conditions, and relatively more reducing and relatively more oxidizing conditions. So on the top left here, you can see the water content in the starting materials, which were relatively low, of about 8 to 50 micrograms per gram water in the original starting material. And then in the other 3 plots, you can see the water contents in the experimental run products. And as you can clearly see, I was indeed able to hydrate my samples. The water contents have increased to about 100 to 500 micrograms per gram water. Interestingly, if we look at the FTIR spectra, so the plot here on the right, we can only see the titanium 3+ related hydrogen defect, which is interesting because some of the samples, especially the chromium doped ones, had high enough trace element concentrations to potentially accommodate a trace element related hydrogen defect, which means then in our experiments, there must be some kind of kinetic barrier for the formation of the other trace element related hydrogen defects. But I want to have a closer look at these 2 that are highlighted here. So the 2 sets of experiments from the same temperature, but different pressure. And this is what you can see here in this plot. So the water contents in the low pressure runs versus the water content in the high pressure run. And you can see that at relatively higher pressure, we also see significantly increased water contents, which shows a clear pressure dependence of the water incorporation into the rutile. But from this experimental data set, we also see other influences on the water contents in these experiments. And these are based on oxygen fugacity and rutile composition. So here on the left, you can see the water contents in the relatively more oxidized runs versus the relatively more reducing runs. And you can see that at reducing conditions, there are higher water contents in rutile. And on the right, you can see a comparison of the water contents in the rutile with the 3 different compositions for each of the runs. You can see that the pure rutile in the yellow and orange has similar water contents as the chromium doped one, but the one with relatively lower amount of trivalent cation impurities has also lower water contents. And this is likely due to the fact that the trivalent cations are majoritively charge balanced by oxygen vacancies. So oxygen vacancies seem to enhance the amount of water that can be incorporated into these experimental rutile. So a quick summary of what we've seen so far. Using polarized measurement, we can get precise and accurate water contents in rutile. We see through peak deconvolution, we are able to identify the different hydrogen defects in our natural rutile. And experiments have shown us that there is seemingly a pressure dependence of water incorporation into rutile. This now provides us with the ability to look into the natural record and try to see if we can actually use water in rutile as a pressure indicator. So for this, I come back to my big natural data set. And here you can see my samples. I looked at a large sample set from different PT conditions, different bulk rock compositions across the rutile stability field. I've done in situ FTIR spectroscopy, and I've also measured the trace element compositions of these rutile by laser ablation ICP-MS. And here you can see the water contents of this entire data set for each sample. And as you can see, the water contents vary strongly from some samples that are nominally dry up to about 2,800 micrograms per gram of water in individual samples or in individual rutile grains. So the lowest water contents that we can see are in granulate facies rutile, with most samples being nominally dry. So water contents below detection limit of about 10 ppm. High pressure granulate facies rutile has slightly higher water contents of about 300 to 400 micrograms per gram. Amphibolite facies rutile and high temperature, high pressure eclogite facies rutile have very comparable water contents, but a relatively high intergrain variability with water contents of about 200 to 500 ppm. Water contents in ultra high pressure rutile are very variable, with felsic rutile is being more nominally dry, and rutile from mafic lithologies having up to several hundred micrograms per gram water. But the highest water contents overall, as you can see here on the left, there's a large amount of blue data points. The highest water contents we see in low temperature eclogite facies rutile, with water contents of above 400 micrograms per gram. However, hydrothermal and pegmatitic rutile, as you can see here on the very right in this pink and purple, have relatively similar water contents as the low temperature eclogite facies rutile. And I will come back to this in a minute, why this is of such importance. First, let's bring our samples back into PT space. So this is what you can see here. The same set of samples in a PT diagram, but this time color-coded by median water contents. And if you compare these two sets of samples, so that are highlighted here in these red circles, you can see rutile from amphibolite facies conditions as well as low temperature eclogite facies conditions. So two sets of samples from relatively similar temperatures but two distinctly different pressures, can see that at relatively higher pressures there are higher water contents in rutile. And for this entire data set, the overall highest water contents, as I've said before, we do see in low temperature eclogite phasous rutile. This means that, as predicted by the experiments, we also do see partial pressure dependence of water contents in our rutile in this natural data set. And on top of this, we can use water contents in rutile to identify low temperature eclogite phasous rutile, so those that are related to modern style cold subduction conditions. So if we do this, if we use, as you see here on the left diagram, water in rutile as a pressure indicator and zirconium in rutile as a very well-established temperature indicator, we should be able to identify rutile from different thermal gradients. And that works really nicely for our metamorphic rutile. However, as you can see here, the hydrothermal and pegmatitic rutile has very similar water zirconium signatures as our low temperature cold subduction related rutile, which is a problem because hydrothermal and pegmatitic rutile are not related to subduction. Therefore, we would like to be able to exclude them from our detrital data set. And for this, we can borrow from what is typically done in detrital provenance analysis. And this you can see here on the right, where we use different trace element signatures to identify rutile from different lithologies. For example, rutile from felsic lithologies has very high niobium contents, and tungsten and or tin contents are enriched in rutile from hydrothermal and pegmatitic settings. So combining this, we were able to develop a new classification diagram using water zirconium ratios as proxy for thermal gradient and total niobium, tungsten, and tin contents as a way to distinguish lithology, which, as you can see here, nicely allows us to identify rutile from modern style cold subduction conditions at relatively high water zirconium ratios and low total niobium, tungsten, and tin contents. But working with hydrogen, we should always ask ourselves if what we're observing is a primary signature or if there's any risk for later alteration due to hydrogen diffusing relatively easily in a lot of minerals. For this, we can look at some intragrain variabilities of water in rutile. So on the left here, you can see two FTIR maps, showing the intragrain variability of water contents in rutile from two low temperature rutile here. And in both cases, you can clearly see that the water contents are zoned. And in fact, if we compare that with laser ablation ICP-MS mapping, so trace element maps, we see that the zoning patterns we observe are relatively similar for the water zoning and for the trace element zoning. And this seems to indicate that hydrogen is indeed retained at low temperature conditions due to the coupling of hydrogen with trivalent cations. Because if you look at this sketch on the right, you remember I told you in the beginning that hydrogen is coupled to different di and trivalent cations when incorporated into rutile. Now, if hydrogen wants to diffuse out of that rutile grain, the charge balance still needs to be maintained. So we need to find another way to get to this charge balance. One way is by also removing an oxygen, so forming an oxygen vacancy for charge balance. And another way is by substituting either the trivalent cation out or substituting a pentavalent cation in. And all of these species have relatively higher, have relatively slower diffusion rates and higher closure temperatures. In fact, for common cooling rates and grain sizes, closure temperatures are in a range of about 600 to 750 degrees, which means that hydrogen diffusion due to this coupling is likely limited to similar rates, meaning that at low temperature eclogite phasous conditions, so for our cold subduction related rutile, hydrogen is retained due to this coupling behavior. And we can also see this when we compare our natural data set with the experimental results I talked about in the beginning. So this is what you can see here. The star symbols, these are my experimental results and also results from the literature. And in the colorful circles, these this is my natural data set color-coded by peak metamorphic pressures. And important, I'm only comparing the water contents linked to the titanium 3+ defect here, because this was the only defect that formed in my experiments. But what you can see here, if you look at the relatively higher temperature range, you can see that the water contents in the experimental run products are relatively higher compared to the natural rutile, which is evidence for diffusive loss of hydrogen out of these natural rutile. On the other hand, at low temperature, we see that the water contents in the natural rutile are at the same level as the experimental results, which again is evidence for hydrogen retention at relatively low temperatures below about 650 degrees. So therefore, we can be relatively sure that the water contents of our cold subduction related rutile are reliable, and we can indeed use this as a way to try to identify modern style cold subduction signatures. Again, a quick summary. Water incorporation into the natural rutile is partially pressure dependent. We see very variable water contents, with the highest ones being in low temperature eclogite phasous rutile. Combining water zirconium ratios as a PT proxy with niobium, tungsten, and tin contents, we are able to identify modern style cold subduction conditions. And these water contents are retained due to the coupling of hydrogen with di- and trivalent cations, which means that hydrogen in trace element systematics in rutile can indeed be used to try to identify cold subduction signatures in the detrital record. Now, before we can move on to actual Precambrian detrital settings, we need to test whether this signature is at any risk of being altered during sedimentary processes. So for this, I've looked at an example from the internal Western Alps. So I've looked at fluvial detrital rutile, modern fluvial detrital rutile, from rivers that have catchment areas in the internal Western Alps that are dominated by low temperature eclogite phasous rocks. So what we would expect from these samples is that they should majoritively show a cold subduction signature preserved in rutile. So here, first, a bit of a description of the samples. You can see on the left a chromium-niobium diagram, which is again used to differentiate rutile from mafic and felsic lithologies. You can see most of the grains I analyzed are indeed mafic, as we would expect for low temperature eclogites. In the middle, you can see a histogram of the water contents. The water contents vary a little bit, but most of them are in the range of about 200 to 300 micrograms per gram. And the zirconium and rutile temperatures, as you can see on the right, are relatively low, at about 500 degrees on average, with virtually all rutile being colder, or recording temperatures colder than 580 degrees. And these signatures are very similar to rutile from metamorphic eclogite samples from the internal Western Alps that I've also looked at. And if we now plot these rutile grains into the discrimination diagram, so again, water zirconium ratios on the y-axis versus total niobium, tungsten, and tin contents, you can see that indeed the majority of these samples has the high water zirconium ratios and low total niobium, tungsten, tin contents that we expect from modern style cold subduction related rutile. Therefore, this is clear evidence that the cold subduction signatures are indeed retained during fluvial detrital transport, which means now we can move on to looking at actual Precambrian examples. So for this, I've started with a case study from the Hebridean Terrain in northwest Scotland, because for this locality, it had been described by Ines Pereira and co-authors that there might be evidence for cold subduction preserved in these rutile grains. As you can see here on the right, they calculated zirconium and rutile temperatures for their samples. And there's this magical line of about 580 degrees, which due to the stability field of rutile, we can infer relatively elevated pressures of at least 1.3 GPa for rutile that formed for rutile that's recording temperatures below 580 degrees. So based on these evidence, the authors suggested that there might be preserved evidence for cold subduction at this locality. And we wanted to test whether with our method we can also see evidence for this. So the water contents here on the left for this sample are relatively low, with most water content, with most grains having water contents below 200 ppm, but there are some grains that have relatively elevated water contents. The temperature ranges between 550 to 680 degrees, with only a few grains in our data set having water contents below 580 degrees. And since we are interested in actually looking at Precambrian cold subduction, I've also dated these rutile grains by uranium lead dating. Important here, we can only look at concordant grains because we are working with single detrital grains, so we can't infer a lead composition. So therefore, we can only look at concordant grains. And you can see the ages range between 1.8 to 1 billion years, with two main age peaks at around 1.5 and 1.7 billion years, with our data set being slightly older compared to the one of Pereira and co-authors. And if we take this data set now and plot it again in our classification diagram, we see that indeed about 10% of our grains do have the high water zirconium ratios and low niobium tungsten tin contents. So about 10% of our grains do clearly record evidence of modern style cold subduction conditions. And two of these grains we were able to date, and they have ages of about 1.5 and 1.7 billion years, which is therefore clear evidence for active regional modern style cold subduction conditions in Eastern Laurentia, so in the source region of these sediments, during the Paleoproterozoic. I then moved on to a second study, or case study, looking at an example in Western Australia. Here looking at modern detrital rutile from two rivers and a beach sample from Western Australia. Again, water contents here are relatively low, and in comparison to the samples from Scotland, the water contents are quite significantly lower as well, with only very few grains having relatively elevated water contents. We also see a much broader temperature range, with temperatures reaching up to 1000 degrees, and only few grains again having recording temperatures below 580 degrees. And again, I've dated these samples, and again, we're only looking at the concordant grains here, where we can see a main age group around 500 to 800 million years, and then a few grains going up to Archean ages. But largely, these grains are Neoproterozoic in age. Here on the left, I've done the same thing with my samples as Pereira and co-authors for their samples from Scotland, where we see the temperature versus age, and also the temperature for the discordant grains as well. And you can see indeed that following this approach, there are a few grains here that are mafic and that do record relatively cold temperatures, from which we could potentially infer relatively higher peak metamorphic pressures. However, if we use our newly developed classification, here on the right, you can see that there are no grains that fall into this field for modern style cold subduction. Therefore, from this sample, we do not have any clear evidence for modern style cold subduction conditions being recorded by these rutile. And therefore, we can say that despite these grains, these samples spreading even in a larger age range, we cannot find any clear evidence for Precambrian cold subduction in these source areas. Therefore, the cold subduction that was clearly active in some regions during the Paleoproterozoic was definitely not globally, but it was rather a regional, very localized cold subduction that was present during that time. So to summarize again, using in situ polarized FTIR spectroscopy, we can determine precise and accurate water contents in rutile. These water contents are at least partially pressure dependent, which we can then combine with other trace element signatures to identify rutile from modern style cold subduction conditions. These signatures are not altered by diffusion and also not altered by sedimentary transport, which means that this classification we can use to find evidence for localized active cold subduction at around 1.8 billion years in Eastern Laurentia. And then now the next step would be to try to fill the record, basically, both geographically and also temporally, looking at other localities, trying to find evidence for cold subductions through this method. And as you can see here on the right in this literature compilation, there are a few examples of localities where we might be hopeful to also find evidence for modern style cold subduction. And with that, thank you very much, and I'm happy to answer any questions and discussions.
Thank you so much, Mona, for this great talk, very comprehensive. You went like from explaining the defects until the different applications. It was really, really interesting. I think people are, we have some internet issues, but they are on the way. I have already some questions, so I will start with these questions and then we can read the comments. I thought it very interesting that you mentioned this, how important it is for us petrologists to have the textural control as well. And I wanted to ask, did you find like for this cold subduction style, some, because you have this variation, did you connect this variation with different stages? Like, do you have some that you can correlate to the prograde to peak or from the heterogression? And do they show like different results? Because let's say during heterogression, you can have the formation of symplectites and coronas. Do they show like something that could be more like composition or controlled, or can you really say it's like a pressure dependent?
So yeah, I've tried looking at that. I've largely tried to look at that by looking at rutile in different textural position in samples. I've not done it for the entire data set. It's a lot of work to try to do this. But I've done it for some samples where I've measured the water contents in matrix rutile and water contents in rutile as inclusions in garnet. So the inclusions in garnet, we can assume that they're more or less unaffected by later alteration because they're kind of shielded. while the matrix rutile might be altered later on. And in low temperature rutile, I don't see a clear relationship. There are very variable water contents in both. But at relatively higher temperature, so high temperature eclogite facies rutile, I have one sample where I did see relatively higher water contents in the rutile inclusions. So that again is for me evidence that there was water loss out of the matrix rutile during retrogression or during exhumation. What I also interestingly see is that there seems to be some chemical control with higher iron contents in the rutile leading to higher water contents. This, from the experiments that I've done, can be due to the fact that there are very high iron contents and therefore very high amount of oxygen vacancies that have a control. But we can actually use this to our advantage because it's a lot of work to measure water contents. It takes a lot of time. You have to go to a different instrument and so on. But this you can potentially screen your detrital data set if you just measure the trace elements first and you use iron zirconium ratios instead of water zirconium ratios, which I've done with this literature compilation at the end as well. This is kind of a way that you can kind of pre-screen your detrital data set if there's any chance for co-production.
Yeah, that's quite awesome. I'm sure Kai wants to talk something about this, so I come back later. We also have some comments from the chat. Yeah, thank you, Mona.
Should we go to the questions in the chat?
Maybe I can read some of the comments.
Because
Rafael Mota said, excellent talk, Mona, congrats. I must admit I don't know much about FTAR, so I'd like to start by asking what kind of sample preparation is required? A polished section?
Okay, so yeah, fair enough. I guess a lot of people don't really know what FTAR is that much. So we can use a lot of different sample preparations for FTAR, but the big problem is that we need, because we measure in transmission, so it's basically infrared light that goes through our sample, and we measure basically the energies that get absorbed by the sample. So therefore we need pure rock sample. We can do this by either using double polished thick sections that are removed from the glass plate. This is what I used for my metamorphic samples. And we can also use double polished single grains. Those we usually then put on calcium fluoride or barium fluoride. Usually calcium fluoride, little discs that are transparent in the infrared range that we're using. And for detrital grains, what works really nicely is just to take the separated grains. You can also do this for metamorphic rocks, of course, but take the separated grains, put them again on the calcium fluoride discs, unpolished, untreated, just directly into the FTIR. Yeah. I hope that answers the question. But I'm happy to explain if there's more.
We have other comments here.
Yeah, he actually has a following question then. I will read the Rafael question and then we go to your question, Hesian. So, also you showed some spectra from HP rocks and hydrothermal vents that display significant differences. Could FTIR potentially serve as a proxy to fingerprint different mineralization processes?
Oh, that's a good question. I haven't thought of it yet in that. I think other chemical signatures are probably more helpful when trying to fingerprint this. I mean, there is so much work done on looking at rutile associated to different types of mineralizations. And what people typically use is tin, tungsten, antimony, vanadium, I think, and other trace elements as well. I think the presence of a vanadium defect for me would be a clear evidence for a hydrothermal or pegmatite rutile, definitely. But the other defects can also occur in not only in hydrothermal, so especially the divalent cation related, so the iron 2+ and chromium 2+ defects, they occur both in the hydrothermal rutile, but also in, I guess you can call them high pressure veins. So metamorphic veins that formed at eclogite facies conditions that are not related to any type of ore mineralization. And there we see relatively similar defects. So it's definitely an interesting idea, but I think there would need to be a more focused screening for that.
Thank you, Mona. There is some comments here from Regiane. Thank you for the excellent talk, really great data and implications. Rutile always provides us with such valuable new insights. And she sent some question. I have a question. Zircon in rutile decreases with the pressure, as in the zircon in rutile thermometer. But you showed water increases. Could you explain why these two trace components show opposite trends with pressure?
Yes, so they're incorporated through different mechanisms, basically. So zirconium incorporation is a direct substitution for titanium 4+, while hydrogen incorporation, and therefore, so it's not really water, it's hydrogen that's incorporated in rutile. We just express this in terms of water equivalent, basically. And hydrogen is always incorporated through coupled substitution. So therefore, two very different incorporation mechanisms. And I think the main difference why we see this pressure dependence for water incorporation is actually it's quite surprising, because thermodynamically speaking, we would expect a temperature dependence. So if you look at the thermodynamic equations, looking at the dependence on water incorporation depending on temperature versus depending on pressure, there's virtually no volume change for the incorporation reaction. So therefore, it doesn't make necessarily immediately sense that there's a pressure dependence. And we're still trying to understand this. So far, I can only say that we observe a pressure dependence. I cannot tell you why. I'm sorry.
So I would like to congratulate you, Mona, also, and read another comments that the people were watching and let here. Great talk, Mona. Congrats on such interesting work. And also from Lucas, great talk. Congratulations. And Rafael was also thanking you for asking the questions. And congrats, Mona. It looks like such a complex work with a lot of small steps, like since the preparation of the samples and the interpretation of the results. And yeah, it's amazing.
Yeah, I also had a lot of luck that things went well. I didn't run into major issues.
But it's an incredible work that you are doing. So yeah.
Yes.
Okay.
Well,
Can I make a comment?
yes.
Yeah. So Mona, thank you for your presentation. Yeah. Oh, I read your paper before, and now it was good to remember. So my comment is, when you show your natural data set, big graph that you have. So, and when we are talking about cold subduction or onset of plate tectonics based on a cold subduction proxy, I can see from the locations of your samples that some of them can be interpreted as a continental collision setting, whereas others as a pure oceanic subduction. So if you take Lago di Chigana, for example, you are talking about like subduction properly expressed by the process of oceanic lithosphere subduction. But then if you go for Doramaia or you go for my examples for Dabishan, we are talking about continental collision subduction. So how can you incorporate in your conclusions these different kinds of subductions? Because when you take like you cold subduction, I think you got from Syracuse or the geotherms, and they are usually from cold subduction like the Cascadian or the Nicaragua subduction or even Japan. And still these continental subduction samples, they fall in the cold subduction, let's say, end member of your natural plot of the natural thing. So do you see any like potential and see how does could affect your conclusions or something like that?
Yeah, so we wanted to look specifically at oceanic subduction. Yes, I do have samples from continental settings, but in the end, from my classification diagram, they are mostly excluded because they are felsic in composition, majoritively. And using the niobium contents, I'm basically everything that so the boundary is you have at least in a felsic rutile you have at least 800 micrograms per gram niobium, following the classification from Meinhold. And the other classifications for that are in a similar range of niobium contents. And I draw the boundary at similar values for the then total niobium, tungsten, and tin contents. So basically through this, I'm excluding everything that is felsic composition of rutile. It would definitely be interesting to get more samples and directly compare the mafic oceanic subduction versus then the continental with more felsic input. I haven't looked at it directly because I've so far just excluded the data, basically. Yeah.
Okay. Yeah, because this is very interesting because it has a big implications how we put the continental subduction and the oceanic subduction in the context of debating how subductions evolve through time.
Yeah, but actually the water contents are very comparable. If I remember, the sample from Lago di Chignana in particular had quite high water contents, I think of about 700 micrograms per gram. So it was high in water. I just think that the niobium contents were then also too high. And as soon as you go to ultra high pressure conditions, so your samples from Mali and the ones from Dabichan and Dohamaira, there the temperatures are too high, so that basically all the water is diffusively lost again. And I had one sample where there were the Lago di Chignana is also ultra high pressure conditions, but everything else from ultra high pressure conditions had less than 300 ppm water, and then also the very high zirconium contents. So therefore the water zirconium ratios are too low. So I guess that continental subduction rutile would probably be excluded from the data set in this case.
Yeah, but another thing that we have to bear in mind, for example, if you have like a oceanic subduction setting, or you have all the metamorphic lithologies, for example, if you take the Himalayas, where you have like Somoriti, although they are inside the felsic granites, you have a metamorphic lithology on like the patterns of metamorphic lithology inside the felsic. And you can have also, for example, oceanic complexes that can accrete to the collision and then being reworked during the collision. So rutile can grow at this period, despite of having an oceanic assemblage. All the metamorphism and everything can be occurring on the process of collision. So this is something also to bear in mind when we do like these whole ideas of how can we use something to disseminate cold subduction.
Yeah, that's definitely a good point. And I haven't really looked into how collisional orogenic settings could affect the water contents, because I just didn't have the right samples for it yet. But it's definitely a good point, and I think it would be really, really interesting to look at selected samples from these different environments, and maybe like get rutile from mafic boudins, get rutile from the surrounding felsic material from these collisional settings, and compare the signatures. And I have to say that I don't really know what I would expect the mafic rutile in this case to record, and also not the felsic rutile, to be honest. I probably expect the mafic rutile to be either too high than in the zirconium when we go to high temperature for the collisional settings, so granulite facies conditions, or they could be, or they should also be relatively low in water contents then. So more like the amphibolite facies signature, basically. Yeah.
So do you have the Himalayan rocks with you or something? No.
I don't have any samples from the Himalayas, no. No, I have from the Eastern Ghats, but otherwise from
if
that
you
area.
want, I can provide you some samples from Somoriti.
Oh, that would be really interesting. Yes, I would love that.
Thank you, Mona. Mona, I was wondering because some, I guess, most of us are not so familiar with the experiments. If you can tell us a bit more about how did you carried out your experiments, and also you said like that some trace elements might have been affected by some barriers, like kinetic barriers. Maybe if you can talk just a little bit about this.
Sure. So basically, what I've done is piston cylinder experiments. So I used synthetic rutile starting materials. I bought them from a company. I cut them into small pieces, and then maybe I can go back to my slide for this to show you the assembly. That this one. So this is the sketch of the assembly, basically. So in the right part, you see the capsule, basically. So this is my actual sample, and the rest is kind of the furnace and the assembly around it to have like a pressure conducting medium and things like that. So what you see is I used the 3 different rutile chips. So they were about 2 millimeters by 2 millimeters and 0.5 millimeter thickness. And I put them into a gold capsule layered with a mixture of silicic acid, and for the reducing conditions, also graphite. So the salicylic acid at the experimental conditions that I ran it at separates into quartz and water. So this way I get water into my system without having to deal with liquid water. And then the capsules are itself also really small. They have a diameter of about 5 millimeter, and then they were about a centimeter long originally. And then you have to close them on both sides and weld them shut. So they get a bit smaller in the end. Then you put them in your piston cylinder, you put them at pressure and temperature, you wait for a few days and hope that everything works. Originally I wanted to have rutile with 3 different compositions, a pure one, a chromium doped one, and an iron doped one. Turned out that the company sold me something with 5 ppm iron as iron doped, which in fact had less iron than the pure one, surprisingly. So the difference in composition between the pure one and what I labeled here as low defect, in the end was that of course a synthetic pure rutile always has some level of cation impurities. So there were a few, I think up to 30 ppm of magnesium, aluminum, a little bit of iron, and then also a bit of niobium, tungsten in there. And if you calculate the charge balance between the diene trivalent versus the penta and hexavalent cations, you can assume that the rest of the charge deficit from the trivalent cations, due to the basically thermodynamic probability of rutile defect chemistry, the rest of these trivalent cations are very likely charge balanced by the formation of oxygen vacancies. So with that, the main difference between the pure and the low defect rutile is the amount of oxygen vacancies that was relatively lower in the low defect rutile. So this way, we can in the end say that the low defect rutile with the lower water contents has a lower amount of oxygen vacancies, while the pure rutile and the chromium doped rutile, which if you do on molar basis the charge balance, have a relatively similar amount of oxygen vacancies. So therefore we can say that the amount of oxygen vacancies is likely causing a difference in the amount of interstitial hydrogen linked to titanium 3+, which is the only defect present in all of these experimental samples, so that there seems to be some influence of the amount of oxygen vacancies to the amount of water that can be incorporated. Yeah.
Thank you so much, Mona. Anyone wants to ask something else? Otherwise, I recommend you that you write to Mona. I'm sure she will be happy to discuss with everybody. And so thank you again, Mona, for joining us today.
Thank you very much for the invitation.
And I want to invite everybody to join us next month. So we are planning to have the PTG talk every last Thursday of the month. And next month we will have Professor Pedro Leonardo Vieira from University of Brasilia. So stay tuned and see you in a month. And thank you, everybody.
Thank you, everybody. Thank you, Kae and Katarina, for joining with us today. And thank you, Mona, for accepting our invitation.
Thank you very
much.
Thank you, Mona. Nice to see you again.
Thank you, guys, and thank you, Mona. Congrats.
Congrats.
Ciao.